right, okay, let's now see what we should do before the reading week. All right. So, reminder, your written test number 1 will be after the reading week. Let's look at the calendar together. If you look at that, we are now here today, the 10th of October. You got a reading week, and then you got your written test number 1 on the 23rd. I will give you some, like a guide, for programming test 1 on Tuesday morning, the latest, maybe tomorrow. Okay, I'll try to give that to you. But I think for now, you can definitely assume this will be the main coverage for your written test number 1. I can tell you right away. It's going to cover for sure the math review lecture. We can definitely finish the last bit in the first 10 minutes or so. So written test number 1, for sure it's going to cover, number 1, your math review lecture. You should definitely start going over all the definitions and also all the example that we talk about. And then the written test is going to be more into the conceptual understanding of the various constructs. And for sure, it's going to cover lab number 1 and also lab number 2. And I'm now considering the possibility over here, I'll let you know, because we don't really have any scheduled lab during the reading week. So maybe I'll shift the deadline for lab number 3 slightly. So you can still ask me some question during the office hour. I'll try to make the TA also available over Zoom. You guys can also take advantage of that. So we can maybe push the deadline slightly. I'll confirm with you, just more time for you. And then for your written test number 1, you don't have to worry about lab number 3. All right? For written test, okay. So I think I'll be more precise about exactly what can be asked about rodent, maybe in the guide. But I would say you definitely don't really have to launch the rodent during the written test number 1. You don't have to. So what you may have to do, you will see some example question I'm going to make available to you guys. So I might say now, for this particular construct, now enter some ASCII syntax that's going to be in rodent, something like that. But you will see when you see the example question. All right? So you will see. Yeah, question?
Sorry, just making sure. So practice questions will be posted as well.
It'll be posted as well. Yeah, so written test number 1. Let me say this. The guide and practice questions available to you. Monday, the latest. If I cannot really make it happen tomorrow, I'll make sure I work towards that on the Thanksgiving. Don't worry. I'll make sure it happens. All right? Question? Yeah. Yeah, I see what you mean. So I would say, let me be a little bit more precise. Since for the written test number 1, you will not be given the event B PDF anymore. So I'll be more reasonable about you shouldn't really memorize too much. Okay, I'll get in touch with you about that. Okay, good. Okay, good. Okay, that's about written test 1. Please wait for my guide either tomorrow or Monday morning or afternoon the latest. I'll make sure that happens. Okay, and I'm going to host our office hour during the reading week. In case you want to talk to me about lab number 3, you can still work on that. I don't think it's going to hurt. And also for your lab number 1, lab number 2 math review, they will for sure be covered in written test number 1. So you can start asking me questions already. Don't wait for the guide. I think it's going to help you. And there will be a bonus opportunity for you guys, right? So I will reach out to you again either tomorrow or over the weekend. So normally I like to do some midterm course survey over the e-class. It's going to be completely anonymous. I would just like to hear how you feel about the course, my teaching, etc. You want to say something good? I appreciate it. But if you want to say something for improvement, I also appreciate it. So it works like this. If the response rate goes above certain threshold, we're going to get some bonus for everybody. So that will be up to the collective response rate from everyone in the class. But I'm going to give you some window of days to actually complete the survey. Well, I'll reach out to you, okay? So it's going to benefit. Either if I can make some maybe adjustment, maybe after the reading week, I'll try, but I cannot guarantee. But if I really cannot, I can consider that maybe for future students. You can also benefit them too, okay? All right, guys, do you have any questions? Oh, one more thing to say. For your programming test number 1, I will meet with the TA tomorrow for sure to discuss the grading rubrics already. So I think I will start grading possibly from Tuesday next week because Monday is a holiday. I cannot ask them to work, so maybe Tuesday. And I'll try to get back to you. I'll try our best to get back to you by the written test number 1. I'll try our best. If no, I will see what I can say maybe on Tuesday's class, what you should know about the programming test 1. Okay? So, no worries. All right, and we can do, like last time, we can do a review session as well over Zoom, to answer your question. So you definitely got a chance to ask me questions, always. All right, so for today, the plan will be, let's finish the last example in the math review, which is an interesting one to see how we can formalize array using relations. You maybe have never thought about it. It's kind of interesting problem to think about. And there will be many related question that we can ask maybe for later. And then after that, we can finally move on to the first case study for the course. My biggest hope definitely is to go over in very much detail with you about a case study. I got 100 plus slides on that, but we're going to go over them very carefully, one by one. There's no rush on that. I'm hoping that at least we can finish the bridge controller in time, and then if we can have maybe 2 or 3 more lectures at the end, we can do the FTP as well in the class, right? That one's going to also make use of the relations functions that we did in the review. But you're already applying them in the labs already anyway. So you definitely have not done any work for nothing, right, so far. So that'll be the plan. All right, let's now do the last case study. Sorry, last example on the math review. And my power is plug on, so we should be okay today. All right. Modeling decision. Okay, so now this is the first question for you. Now we talk about an array, right? If you remember, that's the Java string array, right? You say string, square brackets, A. And now we want to think about how can we formulate this notion about array, right? And just in case you're wondering, let's say, for example, here. We got the names array over here, pretty easy. It's simply like of length 3 in this case. 0, 1, and 2. Right? So this one here is Alan. And this one here is Mark. And this one here is Tom. Let's not worry too much about what if the array is of some complex object like what you did in 2030. Don't worry about it. Let's now say either array of integer will be array of string. Let's make it simple. All right. We got some example array over here. So you can see there are several notions here. We got a notion about indices. And we got a notion about the contents of the array. So if we want to formalize the notion about array, we have to look after these 2 notions. So we got indices. Also, we got the contents of the array. Right? So these are the 2 notions. And let's go back to the original question. Here. So now, should we model this array over here or formalize it as a partial function or a total function? Right, let me write it down. So we're basically saying, let's say, let me just change, you can say names or array. Let me say A, just to be consistent with the slides. You can think about this as array A. A here. Now, how can I formalize it? Option number 1, we say A is a member of a partial function from integer to string. Let's assume string is a carrier set, the set of all possible strings. Option number 2, we say A should be a member of integer and then total function. Let me just make sure I'm consistent with the choices. Partial and total. Right? Partial and total. And hopefully by now you're pretty familiar with the notation here. So this will be partial and this will be total. Now, option 1 or option 2, or you think both are fine. It's not, again, important for you to think about what does it really mean if I choose the partial function, and what does it really mean if I choose a total function? What's the implied property by those two? You think it should be partial? Let me ask you the other way. Why would you think option number 2, being a total function, is inaccurate? It's not good.
Because all the negative indices will have to be matched.
Aha, that's a very good thinking here. All right, so it seems like, Billy, what you just said here, this is not accurate, this is not appropriate, I agree, for 2 reasons. You just mentioned one. Okay? So, number 1, because the integer over here, if you say total, the domain, by definition, if that's a total function, that means the domain of A should be equal to the entire integer set. All right? And then we know that integer does include, for example, so let's say minus A, minus 7, all the way to, 0, and then all the way to here, right? Just the fact that you have included minus indices are already wrong, because array indices always start from 0. Okay? So, not appropriate indices. There is another drawback. Another drawback, which I can mention to you. Even if you say, over here, if I say I want to keep us only from 0 and onwards, basically you're saying, let me give you an intermediate version. 2A, for example, 2B. If I say A is a member of, let's not exclude the negative numbers. What about n? Right? Remember, natural numbers start from 0, right? Which map this case here. This is better, but do you think it is appropriate or not? We don't have enough contents to map. In some way, I can tell you that we do have enough contents here because it's a string, right? It's more to do with reality. In reality, the array has to be stored in the computer, and computer memory should always be limited. Doesn't matter how large it is. So here we talk about integer over here, for example. That one there should be unlimited conceptually, right? So now if you say from 0 all the way to, in theory, plus infinity, we don't have enough space to store every one of them. Just cannot be infinite. Array has to be finite. Okay? So that's another reason. Number 2, natural number and this are infinite. That's also inappropriate. It's got to be finite, and also it cannot contain negative numbers. So these are the 2 things to watch out for. Right? You can see the reasoning process over here. Whenever you want to formalize some programming notion or informal notion, always think about the concept, the construct you are choosing. Right? There's always consequence. That may be something you don't want. All right? Exactly what we said. All right? Now, how about this one here? Now, this one, nothing about right or wrong. I want you to tell me the interpretation. Now, this one here, can you guys tell me what that symbol is, if you remember? Oh, actually, I said that, right? I shouldn't say that in the slides, actually. I should really get rid of it. That should be part of the exercise. Sorry, that's my bad. Okay, let me write it down on the page, and then we'll discuss. Partial injection, right? So now, if I say A is a member of, let's say, integer partial injection string. Okay, let me now move to the iPad. Okay, now I want some interpretation. Of course, you can simply throw the implication that complicated injective property to me, but I want something that's more intuitive. What does it really mean? When I say A being an array is an injective function that's partial between integer and string. So being partial, we already somehow say we may not include the negative number, right? But now, what does it really mean? That's also injective. What does that mean? Different. Yeah, different domain value should really give you a different range value. That I agree. Or put it another way, there should not be any range value that's mapped by distinct domain values. Okay? And what does that mean, even? That means the array does not contain any duplicates. All right, I'm going to visualize that for you, but let's take a look. Let me now just remind you about this because that will also be covered in your written test. So this simply means the same range value not mapped by distinct domain values. And now the interpretation will be the array does not contain any duplicates. What does it really mean when it contains duplicate? For example, if I got A here, that's pointing to an array, let's say this. 0, 1, and 2. All right? Let's say it stores, let's say, Alan. And then we got Mark over here. And also we got Alan over here. So now how do we see that this one it violates the injective property? How do we see that? The way to visualize this would be, think about A over here is like a partial injection. Injection is just like a relation, set of order pairs. So it's like a 0 maps to Alan. And also we got 1 maps to Mark. And finally, we got 2 maps to Alan. So now we are back to the form you're familiar with when we did the exercises last time on Tuesday, right? So now if you take a look, you basically got the same range value over here, Alan, that's being mapped by 2 distinct domain values. That's definitely a violation. So you cannot have any duplicates in the array in order to be a partial injection. That's how you see it. All right? Any question about this? Yeah, you want to think about it. Okay. All right, if no further question, let's now move on. So, by the way, just in case you have confusion, so this over here is not a member of the partial injection that we talk about. Not a member. All right, I'm just giving you some counter examples so you can see why we interpret that as having duplicates in the array. The next one. Number 3. Now we talk about injection. What about surjection? Can an array be modeled as a partial surjection? I'll write it down here. Okay. This one here. Now, if I say A is a member of partial surjection, that means double-headed, right? It's about the range string. Is it appropriate to say an array is a partial surjection? What does surjection mean, if you guys recall? If the range value should be covered, right, in the entire set. Yeah, no worries, yeah. Let's think about the consequence, yeah. I think you guys are really getting there, sometimes just a little bit hesitant. That's okay. So this one here really means the range. The range of A is exactly equal to the string. Does this make any reality sense? String is a carrier set, which contains the set of all possible strings, starting from length 0, length 1, length 2, all the way to length infinity. Do we have that much computer memory to store it? Not really, right? So it's not appropriate. So if you think about this guy here, string is the set of all possible strings. So not appropriate. Just want to know the interpretation. But okay, so here. the slide answer over here was making, let me see over here. I was jumping a bit, sorry. That one, the slide example is about integer over here. So the one I did, okay. This example is still valid. I'll just talk about something different from the slide. This one, valid. Let me talk about also the one on the slide. Sorry, I wasn't reading. What about partial injection in this way? Let's say a member of, let's say, partial surjection, but it's also integer. All right? So here, I think that the slide was making a little bit assumption. Of course, the assumption has to be stated very explicitly. So let's say, for example, if somehow we assume that this will be maybe like an int type in Java, in which case it will be 2 to the power 32 bits, right? 32 bits. Right, 32 bits. So that means you got this many combination of values. If we can make that assumption to say, in this specific example, we're assuming that this guy here really is corresponding to the integer type in Java, rather than the int type in mathematics. If we can make that assumption there, then this suggestion here is possible, because it covers all the integer. All right? So here, if that we can make that assumption, this will be possible, because the array simply stores all int values. Okay, of course, the assumption has to be stated explicitly, which is what the slide does. All right? But if instead, if no such assumption, meaning that the Z over here is the mathematical set of integer. In that case, it will be infinite. In that case, it's not possible. Okay? And then we'll say a member of this partial function this, partial surjection. Yeah, so you always have to see what you can assume. That's important. Not appropriate. Because this is infinite. All right, so it depends. All right, so far so good. Let's see if there's anything else we can see. Okay, that's all. Yeah, that's actually the example I talked about first, about partial surjection to string. And we said that it's not possible because string is infinite, right? No matter what. Yes? Yeah. So are you more talking about 2 or 4? Sorry.
Sorry, I think I guess
2,
2.
okay. What about it?
So then, like, you're mapping a number to a string, right? So that means if it's by reference.
It's a good question here. So the question basically is about, now here when we talk about any duplicates, is a duplicate going to be boiled down to reference equality or equals method, right? It doesn't really say, so here we'll by default just say by comparing the contents. But in the actual test, yes, it will be very clear about what we really mean. Yeah. The reason I'm using a string over here is if I use 2 integers, then it's not easy for you to see which one is the index, which one is the content. So I just want to use a string to make a distinction. It will be content. Yes, that's correct. That's correct. Yeah. I think usually in the modeling, we don't really deal with like a programming concept like an aliasing or maybe things like a reference equality. We don't do that. Just contents. Yeah. Mm-hmm. I talk about number 3? Yeah. Yes. So the range has to be equal to that set. Yes, that's correct. Are there enough domain values enough to indeed, because the domain value there is also integer, right? So now we're just assuming that the domain set is simply just the entire integer. Oh, I see what you mean. That's a good point. Interesting. You made a good point. Let me put a, okay. Okay, I see what you mean. Let me put, it's number 2 you're talking about. So this one here, right? This one here. Oh, yeah, sorry, forgot to switch, yeah. I do see your point. Let me do this. I think there will be some incompleteness on this example. Okay, if you don't mind, guys, let me say to be revised and discussed after reading week. Let me fix that slide and then make sure I say that properly. I do see your point. Let me clarify that and with a more complete example after reading week. I do see your point. That's a good point. Yeah. So guys, just for this one here, you can just ignore that just for now. Just for this particular one, that bullet point. All right? I'm going to revise that and then I'll come back to this one. I'll make sure. All right, so that will be that one there. And then I think the final one here is about bijection, right? So the bijection here, I think that will be a similar issue here. So number 5 as well. I'll come back to 3 and 5 later on. So this will be number 3 and number 5, right? I'll make sure I revisit them with more clarity. I think just assumption there is not clear. Okay, I'll make sure it's clear, and then I'll talk about it again. Not now. If I think on the fly, you'll be even more confused. All right, so now you can pay attention to maybe more about 1 and 2, and also 3. Sorry, number 4 as well. But I think the most important one will be 1 and 2. These are the 2 things you want to focus more, especially how you interpret partial injection to see why that'll be linked to the duplicates idea for the array. Okay. All right, any question here? Very good. All right. So the math review lecture is basically done. And then I do have some slides there showing some exercise you can try. Here, I want you to go back to that where is example, the first modeling exercise we did. And now I want you to go ahead and think about what does it really mean when we have employee and also location, but now rather than just thinking about relation, partial function, total function, what about we talk about, let's say, injection, surjection, and bijection? What does it really mean? Think about it, okay? And then review all the examples, except for those 2 bullet points, which I promise I'll come back on Tuesday. Not next Tuesday, after reading week. Okay. Any question here? We're good? All right. So I would suggest today we'll take a slightly earlier break because now we're just done with this lecture here. Why don't we take attendance now? And then we'll start the fresh lecture after the break. Okay. Let me pause the video now. All right, so today is more like an introduction to the bridge controller. We're going to stay here for a few weeks at least. But this example here is going to be very self-contained. That's going to teach us many, many good stuff. Refinements, sequence calculus, and also invariants, many things that you also learned back in Lab 1 and Lab 2. But not too much about relations, function, etc. It's simple numbers. But even that is going to give us quite many challenges to reason about. So we're going to stay in this example for quite a bit. So I try not to give you so many slides in the beginning, only one chunk at a time. So once I pass through the current chunk, I'll give you another chunk. That might be better. So let's see what we're going to learn. So today is mainly about some introduction, and then we'll see the first abstract initial model to see how simple it is, but at the same time, how valuable it is. Okay? So we'll talk about requirements document. It's a very quick review of what you learned in Lab 1. Okay, and we talk about refinements, but maybe not today, but we just mentioned about in the big picture how the refinement is going to fit in. And formal specification, of course. And we got static context, constant axiom theorems. And also we got machine, variables invariant, event, Gauss action, right? So these are just what you have already seen, but just a different example. proof obligation, right? Especially invariant preservation. Later on in the lecture here, we're going to make the proof obligation more like a sequence style, which means every time we want to prove a particular stuff, it's going to be specified in terms of sequence, something very formal, in order for us to prove it. Of course, there are two outcomes here. Either you can prove it or you cannot prove it. When you can prove it, great, show me the proof. When you cannot really prove it, that might give you some good insight into the system about maybe somewhere in your model is wrong. You got to fix it. Okay, that's something we'll see. Maybe not today, but later. Yeah, so proving refinements and also proving properties. Properties here is more about invariance. Invariance is really everything that we care so much. Inference rule. We don't have that many inference rules, so we just want you to get gradual, like a developments of the example. We'll introduce set by set for the inference rule. All right. Anyway, so that's kind of like a summary of what we're going to see. But there are many more details that cannot be summarized in the learning outcome. But these are the big items we're going to see. All right. Very quick reminder about correct by construction. All right. So basically, something like this, right? You remember the diagram here? I'll only spend a few minutes just to remind you, because we're going to see this in the bridge controller. Okay. So what we're going to see is this will be the initial abstract model. Initial, most abstract model. All right, and then from this initial most abstract model here, we're going to see some intermediate one. For example, we might have M0, and then we get to M1, and also we get to M2. This is what we're going to see in the bridge controller. We only got 3 models to show in the lecture. So what you want to know is when we got the arrow here, so that means M0 is refined by. All right, and then, so the idea will be we want to somehow, 2 things. In M0 here, it's the most initial abstract model. Number 1, do not include all variables and constant here. You only choose a subset of them to put here, some very simple one to begin with. Only a few at a time in each model. In each model. And number 2, the consequence is the properties that we have to check in each model will not be so infeasible. It'll be quite feasible for us. So number 2, in each model, the number of proof obligation to prove is manageable. All right, so let me say a little bit more, and that we should be okay about the review here. But you can also see the slides. That's basically more like a repetition from the introduction lecture. Over here, if we look at, let's say, somehow Mi and Mj, right? And Ij here can be, for example, 1 and 2, right? Like an M1 and M2 over here. You want to think about here in Mi or M1, you want to prove some properties. You don't need to prove all. That's the main focus. And then when we say we want to refine Mi to Mj, we usually will try to add more constants or variables. And now in Mj, in the subsequent refinements, there are 2 things we got to prove. Number 1, we want to prove additional properties. Because we got more variables, so we should definitely put more properties, right? But not too many more. The idea would be you want to make every model there not too large in order to be feasible, to be handled. Number 2, prove that MJ is a formal refinement of MI. So here, when I say formal refinements, there will be some proof obligation we had to see. For now, you don't need to worry. Just remember there are 2 things you got to prove in each subsequent refinement. Number 1, you got to prove any additional properties that will be a result of the additional variables we added in this refinements. Number 2, we got to show formally that this is indeed a refinement of that. That's something we have to discharge as well. But this wouldn't come until a little bit later in the case study. We're gonna finish M0 first before we see how M1 is going to refine M0, one at a time. All right? I think that's about what I want to say. Correct by construction, but you guys can review just the slides to see what to say more. Okay. Now state space, which is important. All right. So what's really a state space? So state space is basically the set of all possible configurations. Well, we can see some example. The more variables you have, the larger the state space it is for your model. So you really don't want to have the initial model or subsequent model to be too large in its state space. When the state space is too large, it's just too difficult to comprehend and handle. Okay, we can, and of course, in each configuration in your state space, you also have something like an axiom, invariant to really make sure it's kind of confined into certain values. We're going to see an example right away. Okay, let's see this. All right. Right, you can read a definition about a state space, right? That's something you can read. But let's see example here. Let's say this will be the specification for our state space. We got one constant, which is positive. And this, by the way, is very relevant to lab number 1. So that's why I chose it. It's easier for you to link. We got some credit limits, positive. We got some limits for your account, upper limits, which is also positive. And we got some accounts, partial function between the string and also the integer, the balance, basically. Okay? If you only got this, you have no limits on, upon the credits and also the, let me say this. This alone typing constraint alone does not restrict the variables and constant to the legitimate value. To legitimate values. Okay, let's see what's going to happen if we add in this particular constraint, which is an invariant desired property. At least let's see some example configuration, and then we'll see without those configuration, what can we have? That might be easier. All right, so question number 1. Let's give some example configuration, okay? We can do, let's say, initial configuration. When the system is first initialized, so it's going to be basically, let's say, configuration is usually an order pair, okay? So we have, let's say, the constant over here. Let's say, what should be the credit limit? Can be any positive number. Let's say 10,000, for example. That's the limits. Also, what should be the upper limits? Let's say 20,000. And then, also, we got the account. Let's say account initially is simply just empty set. Right? If you remember the initialization events in your lab 1, empty set. This is one valid configuration. All right? And configuration number 1 could be, let's say, we still have the same constant here. But now we do have some account. Let's say Bill. Let's say Bill is the owner, and then it will map to, let's say, for example, 5,000. Right? This is good. It's a single, this is a singleton set, which is completely okay. It will just be from Bill maps to 5,000. It's valid. It is also going to satisfy this particular invariance, because you can see the 5,000 is in between minus 10,000 and 20,000. Agree? Okay, you can see the idea. Of course, you can keep adding more clients or more accounts into the bank and just make sure every one of them is just going to satisfy this particular constraint. All right? Now, let me give you something that's illegal. And this one will illustrate why it is important to always have some extra desired property to make sure your configuration is valid. So let's say this. What if, so typically this guy here will be the invariance. This one here will be the invariance. What if no invariance? In that way, we can easily have another configuration over here, for example, C2. In that way, we can say 10,000 still, and we got 20,000 as the maximum limits. And now, let's say we still got Bill, and now he may just got minus. So the balance will simply map to minus 50,000. Right? You can see this one apparently is not legitimate, because you can see this one here, minus 50,000 is not between minus this and plus this. Right? So that's why having this invariant over here is so important to constrain the value for the order pair. Right? All right, so now, so far I'll just give you an example, but now we want to make it more precise. What does it really, so we just give you individual configurations. Your state space is going to be all the possible configurations combined together. How do we formally specify that? Remember the set comprehension expression that we learned, right, in the math review a bit while ago, but let's now try that. In general, you can think about given some typing constraint for the relevant constant and variables, and given the desired property, you can specify as follows. You can say the state space is basically going to be equal to a set over here. All right? The set there is going to be the variable and also constant list, separated by comma, or just order pair, basically. I'll show you an example to this one specifically. And then, what should we specify as the constraint over here? Right? That's important to say. Right? We want to put both the typing constraint and desired property, or invariance. This is how you can understand it. You can think about the typing constraint must be satisfied and is a conjunction, desired property. And also the invariance, desired property. Right, so both have a role in the set comprehension. So once we got all these and combined with all the possible variables, we can figure out a state space conceptually. Okay? So you want to say, without invariance, the resulting set is much bigger. Because you can see that this is a conjunction over here. If I got stronger invariant, just more invariant, the more invariance I got, the more I can make this one here filter out more illegitimate values from the configuration. So that's why this invariant here is important. All right, a final exercise to do is to say how we can specify this guy specifically as a set comprehension. That'll be it, right? But it's so important for you to understand the state space. All right, final exercise. For this particular system here, I'm going to put it here. The state space is going to be like this. We got C, we got L, we got accounts. So we got C, we got L, and we got accounts. Right? It's an order pair. Such that, and then we're going to have the typing constraint. So C should be a positive number, and also L is also a positive number. And also the accounts, I'll say EECS just to save my writing, is a string partial function to integer. And finally, you'll be AND. So this particular part over here is invariant, right? Just imagine that I'm going to put invariant here, right? So that'll be the set comprehension. Yep. But it's more important for you to understand this set comprehension expression here. This one is more important, more general. Okay, very big, basically. And for one very important remark to make, comparison between 3342 and 4315. Okay? So as I mentioned in the very beginning of the course, the approach we're adopting for this course is called theorem proving. When you're proving stuff on the paper, having a very large state space is not too big an issue because you're proving. You're generalizing certain things. It's just by applying inference rule. So it's not too bad. However, having a big state space is a big bottleneck for what you're going to do in 4315, which is called model checking. That's something we'll see later. But for that, I want to make a quick remark. And there is one keyword I mentioned in the slide. I want you to also pay attention to it. It's something called combinatorial explosion, meaning that the more variables you have, the larger state space you're going to have because of combinatorial multiplication of the variables. And sometimes people also refer this to state explosion as well. So state explosion is not too big an issue for this course here, but it's a big issue for 4315. Let me say that, the final remark, and then we can move on. Okay, so the state space over here is a bottleneck for model checking. Of course, you wouldn't know what model checking is. That's okay. That's something you will learn in 4315. All right, that's just a remark. All right, any question about this? Right, conceptually pretty simple. You just want to know how you can visualize, visualize the state space. Right, we're going to see example as well, hopefully today. All right, and this bullet point here to say the more concrete your model is, meaning that if you go back to correct by construction here, if you go this direction here, that means, oh, let me just make that notion here. If I go from left to right, if I go from left to right in this direction over here, that means your model is just becoming more and more concrete. More and more concrete model, right? And more concrete model simply means you got larger and larger state space. And it's going to make your verification more and more difficult, especially model checking. Right? I just want to focus on state space. More and more concrete, that means larger and larger state space. Just more and more variables, basically. Larger and larger state space. All right, good. Let's now move on. Good. All right, so now let's see some quick roadmap. We're getting to bridge controller very soon. And we're going to see the bridge. And then it's actually an example of reactive system. We're going to have some sensors and actuators. But in the initial model, not really. But as we see more refinements, we're going to see more sensors, actuators, and traffic lights. That's what we'll see. Reactive system, sensors, actuators. So now the roadmap is going to be like this. So we got requirements document. We're going to go over today. We got some E description. We got some R description. And we have some refinement strategy as well. So that means each model is only going to cover some subset of the requirements. It's not going to cover them all. That's the idea. And then initial, we got a most abstract model, and then we got first refinement, second refinement, third refinement. Most likely only we're going to see 2 refinements. Okay, most likely. All right, so now the problem can be something like, the Toronto Island. You got a mainland, Toronto downtown, and also you got a Toronto Island, right? So let's say rather than taking a ferry, we want to build a bridge, for example, right? Or any context where you have a mainland, you have some island, you want to build a bridge between them. That's basically what you want to do. All right, let's take a look at the E description, R description. We can now understand the problem a little bit more. Let me now go directly to here. We got E description 1, 2, 3, 4, 5. So these are the environmental constraints. Nothing we can do about it. We somehow have to code them up into maybe assumptions into our model. Maybe axiom, maybe some variables, maybe some constant. We'll see. So let's say E description number 1. So the system has 2 traffic lights with green and red. We'll see them later. Okay, so 2 states basically for the traffic lights. Okay, 2 traffic lights, and then in E description number 2, the traffic lights control the entrance to the bridge at both ends of it. What does that mean? So basically, you say this is the bridge, you got some traffic light here, you got another traffic light here. Okay, on the 2 ends. And the cars are not really supposed to pass on a red traffic light, only a green one. You know what? This E description here sounds a little bit like a dump. Isn't that always true? This is actually a very important assumption. Because later on, when we get to the second refinements where we got traffic lights, when we prove some safety property, assumption about number 3 is very important. Because we're assuming that if we cannot assume the driver will actually obey the traffic lights, then whatever we prove doesn't make sense anymore, because driver can just go across the red light, in which case they just have collision anyway. So the bridge control is never safe, right? So that's an important assumption. So this one here is really important assumption for safety property. Right? I should really write on the white space, sorry. That could be hard to read. Sorry. So this is a very important assumption, even though it sounds very simple. So environment number 3 will be important assumption for proving safety property. To prove safety property. Oh, by the way, there's also a diagram I can show to you based on what we have seen so far. We have some island, we have some mainland, and there's only a single bridge we have. Ultimately, we're going to introduce traffic light on both ends. Ultimately, not in the initial model, but ultimately. All right, so now let's move on. And environment number 4, the system has 4 sensors with 2 states, on and off. So you can think about there's going to be some sensor over here, sensor over here, sensor over here, and sensor over here. Somehow, when the cars enter, when there is any car enter from the mainland to the bridge, the sensor is going to somehow count, somehow, right? And also when the car actually go from the bridge into the island. That's going to be another sensor. When the when the car actually leaves from the island into the bridge, and when the car actually goes back to the mainland. There are just 4 sensors over here, okay, to maintain some counts. Okay, so environment number 5 is just about what the sensor is supposed to work, right? That's something we'll get into. Right, so far, these are all the environmental constraints, and they should be somehow reflected into the model, okay? And let's see the requirement that what we have to make sure it works, intended functionality. The bridge control system is controlling cars on the bridge connecting from the mainland to an island. That's exactly what we have seen over here, right? That's the bridge. One way. Okay. And requirements number 2, the number of cars on bridge and island is limited. All right? So this here specifically is the requirements we're going to focus on only for the initial model. This is the only requirements to focus on in the initial most abstract model. That's something we're going to see. Okay? We just use some very simple integer variable. So the state space is very small in the beginning. And in the subsequent refinements, we're going to have requirements number 3 come into play. So the bridge is one way. Okay, so this will be some refinements to introduce. Introduce to the initial model. Right, so we don't really do these 2 requirements at the same time. We do one at a time in separate model. And prove that the subsequent model that handles requirement number 3 is a formal refinement of the initial model that handles requirement number 2. That's what we're going to see. Right? It's a rather small system, but it really shows how you can handle like a big projects. But let's see how things are going to go. All right, if no question, so let's now move on. So today is mainly introduction, just to give you as much information as possible. So when we come back from the reading week, we can get to the more mathematical part about the bridge. All right, let's now move on. Let's see. Okay, still have some time. All right, E description we went over, and also R description we went over, and that's a diagram here. But in the initial model, it's actually simpler than this diagram. This diagram is already too complicated as an initial model. Refinement strategy, right? For that one there, I'm not going to say too much. That's something we can keep revisiting. What you need to know is for the initial model, which we'll introduce today, that one there is only going to handle requirements number 2, only that one. And again, a reminder, requirements number 2 is really about the number of cars on the bridge and the island is limited. So we want to make sure whatever car is here and here, they are limited somehow. We're going to model that, okay? Only that. And for the subsequent refinement, we're just gradually adding more requirements to be handled, right? You can see the subsequent refinement, etc. Right? I would say come back to these details once we have seen the refinements details later. Right? That's a reference slide that we can revisit later. More like a summary slides. But again, remember, correct by construction. We're only doing some manageable properties at a time in each model. So we don't try to do everything in a single model. Okay? Correct by construction. All right, now let's get to the initial model. Okay? All right. So in the initial model, we don't really consider bridge. It might sound a little bit funny. We are building bridge controller, but we don't even consider what a bridge is in the initial model. All right? And we don't consider any sensors. We don't even consider any traffic lights. We consider something very simple. We are focusing on just this single requirements, just about how the number of cards between the bridge and the island is limited. That's the only thing we're doing, just one requirement. And this is an analogy I want you to think about, okay? So this will be the accurate diagram for the initial model over here, okay? Number one, you should see, okay, there's no bridge. And imagine you're trying to see from very high on the sky. Because you're so high on the sky, you're so abstract, you don't really see the bridge. Bridge might be around here, but it's just invisible to you because it's so high up in the sky. Okay, you don't see that. So somehow we are really considering the island and the bridge are collapsed into one single chunk over here. We don't see the bridge in isolation. Okay. And over here, we're just going to introduce some number over here, n, which will be the number of cars in the island and the bridge. And we call this the island bridge compound. That's what you'll see in the slides. Island bridge compound. All right. And let me give you some quick example. Imagine this. Let's say if you have over here, I got an island. Let's say I got a mainland here. And I have the one-way bridge, let's say. Let's say at the moment I got, sorry, let me just annotate this. This is the bridge, right? Let's say at the moment I got 3 cards. On the bridge, they are basically passing through, and they are heading this direction here. Let's say over here. And then we got maybe 100 cards already on the island. This may be what the reality is, but as far as the initial model is concerned, we are treating island and bridge as a simple compound. Okay, so now we'll say n, the number we are talking about, is equal to 100 plus 3, which is 103. That's important abstraction we are making. We are not distinguishing between the bridge and the island, considering them all together. Only in the first refinement, we're going to talk about the separation between the island and the bridge. Not yet. All right, so I would say so far this is the most important information to notice for initial model. Otherwise, you might be wondering, where's the bridge? We don't really have the bridge just yet. That's intentional. Okay, question? Sure, of course. So you mean for this refinement, for this model? Yes. For this model here, we're only worried about requirement number 2. That requirement there to say the number of cards on the bridge and the island is limited. So you can think about we're considering bridge and the island over here. We're considering them as non-separable in the first model. We'll only separate between the bridge and the island in the first refinements later. Okay? In the M0 initial model, consider them not separable. Okay. All right, let's now take a look at the state space to see how we can model them. State space. We got a static part, we also got dynamic part. Let's see how much we can do today. I got about 10 minutes, okay? We're editing time, but let's see how much we can do. So you can imagine that after the reading week, the lectures we're going to dedicate to this case study here, every time we're going to discuss the modeling part about what we introduce in the model, and we're also going to discuss more in detail what the kind of property we're proving about the model. That's basically how it goes. Not just pure math, but we're going to use math to help us reason. That'll be after the reading week. Let's now see just the state space and go over that in detail quickly. Again, let me remind you, we're doing requirement number 2. Okay? And we don't distinguish between the island and the bridge. We're seeing from very high in the sky. Okay? We got only one single constant d. And the d here tells us the maximum number of cars. Right? If you see the slides, you can also see the interpretation. Let me just show it to you. So we got a constant that denotes the maximum number of cars allowed in the island bridge compound. Okay? So we're saying that in this particular bridge over here, we are recording some number there, which is d. And d itself should be maximum of cars in island and bridge. And d must be larger than or equal to 0. Right? Of course, like in your lab number 1, you can easily declare a theorem to say d should be larger than or equal to 0. Right? You can do that too. But let's say we don't worry about it too much. So we got one constant here. And we got another variable. And the variable here to say n here is basically the number of cars currently, meaning that it might change over time. Currently on the island bridge compound. And you can see that very clearly in the invariance here. Right? Invariant is something that we want to make sure it always holds. N should be also a natural number, which means it should also be larger than or equal to 0. And most importantly, it must be limited, right? Meaning that we're going to have n less than or equal to d. So now we got d here, and also we got another variable called n. Current number of cars in the compound. And we got an invariant to say d should be less than or equal to n. Initial model is very simple, but simple enough for us to argue some interesting properties already. And we haven't seen the events just yet, but we'll see maybe a little bit before. We still got some time. Okay. All right, so this is the state space for our initial model. Just one constant and one variable with some nice axiom and also invariant to really restrict about what the legitimate values should be for the state space. Okay, let's now do one more, and then we should be done. Okay. So this is what we just talked about, the state space. And then let's now talk about some possible events. And you can think about events are simply just state transition. So this will be the state space. And you always want to treat invariance very seriously in the sense that you want to make sure every state that's possible from your system should really evaluate true on the invariance. Must hold true on every state of your system. And let's now propose to you some event design. Let's say we got two events. One is called ML out, the other one is called ML in. Okay? What does that mean? The convention goes like ML simply means mainland. Whenever there is a car that actually goes into the island, we say it's ML out. Whenever there's a car that goes out of the compound, we say it's ML in, because they go back to the mainland. ML out, ML in. Right? You can see the direction pretty clear. We're only considering these two events. Can be this simple because the state space is also simple. And now we got some very naive counter here. Whenever we got ML out, it's going to be n plus 1. Okay, let's say for example. Let's say the initial count is simply 0. Let's say n is equal to 0. And then after the first ML out, and n is going to be incremented to 1. And then after the first MLN, it's going to be decremented back to 0, and etc. Right? That's the intuition that we have. And what we really want to identify informally is, are these two events currently designed properly so that the invariance will always be maintained in every possible states in the system? That's the question. Okay, I'll give you one hint. Why don't we say that D is simply 2. Maximum number of cards in the compound is 2. And then N is initialized to be 0. Let's say initially we got no cards in here. Do you think the current design for the events are good or not good? If you don't think that's good, you got to give me a counterexample to say how can we reach a state that violates the invariance.
If n is initialized to 0, but there is no number in MLR.
Well, n definitely can be initially 0, right? Now, why don't we try to do that very quickly, right? I got about 4 minutes. Should be good enough, all right? So let's say here we have our initial states. N is equal to 0, and D is equal to 2. That's the initial states. And for this one here, if you try to evaluate the invariance, N is a natural number, indeed. N less than or equal to D, 0 less than or equal to 2. Good, all right? So we can say this one is a safe states, initial states. So this one here is safe because if you plug into the invariance, 0 is a natural number. And 0 less than or equal to 2 is also true. Right? That's safe, initial states. And if you try to have one event happen, let's say, for example, ML out. ML out over here, let's say if we have one ML out occurrence, ML out is going to have another state over here where the constant D doesn't change. But N right now has been incremented from 0 to 1 because you see N has become N plus 1. Right? That's what you learned from lab number 1. Right? Is this a safe state? It is, because you can see we still have N being 1 is a natural number. And also 1 less than or equal to 2. Right? This is also safe. So we're just doing some simple exercise to see how we can evaluate a safe space to see if that satisfies the invariance. So now the question for you. Given the current design like this, is it ever possible to reach to a state that's not green, that's not safe? Is it possible? Yeah. Yeah. Yeah, that's definitely one way. Yes, your classmate was absolutely right. So that could be one. Let's say once we initialize this, and then we call MLN right away. In that way, N will be decremented. It's unguarded to -1. Now, -1, is it a natural number? Not anymore. All right, that's right. What about, so that means this MLN is not designed properly. What about ML out? Is it okay? Yeah. Yeah, exactly right. Simple, but let me just finish that and then we're done for today. If I do ML out, another one, so this one is going to have D equal to 2 and equal to 2. I got one more ML out. This one is going to have D equal to D equal to 2, never changes, and equal to 3. So far we have, oh, no. This one here is still fine. Because 2 is less than or equal to 2. As soon as we get to this one here, it's no longer good. Because when we try to evaluate the invariance over here, right? So 3 natural number, that's fine. But when you say N less than or equal to D, 3 less than or equal to 2. This one here is already false. So this is so-called invariant violation. Two things I want to say. When you try to do theorem proving, you're going to run into some proof obligation undischarged, unprovable. That's where you can see how the invariant violation is going to occur. That's in this course. When you get to the model checking course in 4315, the way error reveals itself is a bit differently. When you try to check your system, what the model check is going to tell you is it's going to give you a system trace to say, well, if you do ML out, ML out, ML out, you're going to reach this state. That's illegal. Okay, but they got to tell you the similar insight into the system. All right, so I would say during the reading week, maybe you want to review the math lecture, and then that's the most important thing. I'll give you the guidance about the written test number 1. And for the bridge control, just review after here. Just make sure you understand this. We'll dive into more mathematical part and calculus when we come back. All right. See you later.